Good morning, students. Today we are going for lesson 3 of digital communication. In lesson 2, we have seen instantaneous sampling. I'll run through this very quickly. We have seen there were a series of instantaneous pulses and there were mathematical representations, and we finally found that by low pass filtering, at the receiver end, the basic baseband signal can be recovered, right? And there was a Nyquist criteria. That means the sampling frequency must be at least double the frequency of the baseband signal. What was the problem? Why are we discarding this idea? This idea is a good idea for explaining the principle, but the problem is a perfect impulse. That means a zero width pulse cannot be created by electronics. It has to be some width, maybe a microsecond, maybe a nanosecond, whatever it is, it must have a width. And also, if the pulse width is very, very small, the energy content of each sample will be too low for any use. You put it into any circuit, the signal will be lost, right? So what do we go do? We go for natural sampling. This is natural sampling where the sampling pulses are a pulses of definite width, right? And this width, say, is TB. That means bit width is the TB, which also again narrow, but it is a practical width. Now, if we multiply these pulses with these baseband original signal, analog signal, then of course our product multiplier output will be like this. That means for during each pulse, there will be a measurement, and of course, top of the pulse will be exactly like the time domain curve of the baseband signal, right? Where the signal is going down, the top of the curve will be also going down. So this will be the product. Now go into mathematical expression for this. This particular sampling function, that means a train of pulses, you might have done in your mathematics class or in your analog communication class. This pulse is represented by this function, where it has got a DC component, which is actually TB by TS. TB is the pulse width, TS is the pulse period. And then there is an infinite sum of a particular function. Now, what is this particular function? I shall explain you. It looks very threatening, but it's not so. Look at this. This is cos 2 pi, you forget n, cos 2 pi t by ts. That means it's a cos omega t by ts function. That means it's a cosine function. And this cosine function, amplitude of the cosine function is given by this, right? And this amplitude also has got a two part. One part is a constant part, 2TB by TS. Another part is a time domain function, right? This is a sampling function, they call it in mathematics. The sampling function is given here in the bracket. Sampling function x, sampling x is equal to sine x by x. It is once again, it's a variable. So when sampling function, this is, you see, it depends upon the n. That means for n equal to 1, it has got a particular value. And that multiplied by 2TB by TS gives the amplitude of this cosine function. And this sampling function, if you see in your mathematics books, you will find sampling function, the value of the function decreases as n increases. That means in a while, it will be a DC component, and there are infinite number of cosine components of various frequencies, and the amplitude of those frequencies will gradually die down. That means the amplitude of the first harmonic will be very high, second harmonic will be low, third harmonic will still lower, like that. Then if you multiply ST with or MT, then naturally you get this function where MT is multiplied by everywhere. Once again, you find if we can filter out this part, that higher frequencies, we get the baseband signal. Once again, so this is the original signal MT is this multiplied by a scalar, right? Once again, the original signal can be reconstructed by simple low-pass filtering of the sampled output. That is the idea. Then you go to third part, which is called flat top sampling. Why? In our earlier part, this sampling pulses and then creating a product like this, that means the top of the pulse will be according to the curve of the signal is very difficult to obtain in a circuit. So we go for flat top sampling, which is a simplified design, but it introduces some distortion. We shall see how that distortion comes, right? This is a flat top sampling where this is your baseband analog signal, time domain signal, and with some very narrow instantaneous pulses, we sample the signal at regular intervals. Then with the help of a circuit, we create a pulse, wider pulse of that particular sampled value. So top of each pulse is a flat. This circuit is simpler. Each sample is converted into a square pulse of width TB by a simple digital circuit. A simple flip-flop, one single flip-flop will solve the purpose. Now, this is a scheme. We are now analyzing the actual sampling, and I'll try to explain you why a distortion comes. Here is our original signal. Delta is a circuit which multiplies the signal with the pulse train or with the instantaneous sample pulse train and created this kind of a instantaneous measurements. Then HT is another circuit. HT is another circuit which converts these instantaneous pulses of different varying amplitude into a wider pulse. Then at the receiver end, we got a low-pass filter. For the purpose of analyzing the circuit, you can always, frequency domain analyzing of the circuit, you can always interchange the position of the circuit elements for frequency domain analysis, only mind it, not for time domain analysis. So I bring the low-pass filter forward, and this is the HT, which converts a narrow pulse into a wider pulse. Now, here, input to HT is 1 by Ts MT that we have seen in our mathematical representation. You can forget 1 by Ts, any simple, any scalar multiplied by MT, but it's a narrow pulse measurement, which will be converted to a wider pulse. Now let us focus on the transfer function of this particular circuit element or circuit box HT. What is its transfer function? This HT, output of the HT is VT, that is final voltage. Now, this is the time domain representation. Its Fourier transform will be a frequency domain representation. Input will be 1 by Ts AMF, frequency function, output will be VF. And in place of HT, we shall write HF. This time domain transfer function will be replaced by frequency domain transfer function. This frequency domain transfer function, what is the frequency domain transfer function? Is simply the Fourier transform of the time domain transfer function. I hope you have done this mathematics already. Frequency domain transfer function is only the Fourier transform of time domain transfer function and vice versa. Time domain transfer function is inverse Fourier transform of frequency domain transfer function. And this is equal to TB sampling function pi FTB. That means frequency domain transfer function is a constant. You forget this constant, but there is a sampling function. This sampling function is notorious. It creates a problem here. What is the problem? Let us see. This was our output. Is a frequency domain function of the signal MT, but it is amplitude of this signal is multiplied by a sampling function. That is where the problem starts. This is our MF, frequency domain representation of the signal, which is band limited to FM, and this is the, hypothetically, these are various amplitudes of various frequency components. And this sampling function, this function looks like this in frequency domain. That means the value of the function is highest at 0, and value of the function goes on decreasing as the frequency increases. And at 1 by TB, sine pi f 1 by TB, so it becomes sampling function pi f, and sampling function pi f is 0, because sampling function pi f is sine pi f by pi f. So it is 0. So in short, this is a kind of a amplification factor. It gradually decreases, and we find, so obviously, this function, when it will be multiplied by this function, the higher order frequencies amplification will be less. That means, suppose you are listening to a song. At the low frequency voices of the song, you will hear it properly, but higher frequency voices will be subdued. Amplitude will be reduced. So you will automatically understand that there is some problem with your radio or your amplifier or whatever it is. Higher pitches are not coming. Now you have heard of equalizer, which is an amplifier of having amplification, different amplification at different frequencies. This is the distortion, and this distortion is less. Looking at the sampling function, if 1 by TB is much, much larger than FM. That means TB has to be very, very small. And what is TB? TB is the pulse width. So pulse width has to be very, very small. And there will be no distortion if the TB is 0. That means we are going back to the instantaneous sampling, where the sampling pulses are not possible to produce by electronic circuit. So we are in a catch-22 situation. We cannot, that means we have to live with some kind of frequency distortion. And there is and this effect is called aperture effect, because we are measuring the sample for a certain duration. Maybe the duration is very small, but for a certain duration. Like you are, instead of taking a snapshot in a camera with a camera, you are taking a video sample for a few seconds. That is why this effect is called aperture effect. And there is a remedy. The remedy is use a pre-emphasizing equalizer. What is pre-emphasizing equalizer? It's a kind of amplifier whose amplification factor is different at different frequencies. So if you have an equalizer whose amplification is higher at higher frequencies, then This original signal will be higher frequencies will be amplified, and when that is reduced by the sampling function, if you design it properly, then this distortion will not be much, will not be very small. So this is flat top sampling and aperture effect, which is a frequency distortion at higher frequencies, and remedy is pre-emphasizing equalizer. Today we shall go to pulse amplitude modulation, which actually is a part of pulse transmission, and that we shall take in the next day.